Okay, we're going to combine this idea of the binomial theorem with, well, probability, as the name suggests. So basically we're looking at a situation where an event has only two possibilities, and if you think about it, every event can be broken down to two possibilities. Either it happens or it doesn't happen. So you can always split it up into two possibilities, and the event is repeated. So this would be something with replacement, because the probability's got to stay the same every single time. Well, if I did it once, A could happen or B could happen. And we'll say the probability of A happening is P and the probability of B is happening is Q. We do it another time, and I could get AA or AB, or BA or BB. And the probabilities then would go P squared, PQ, PQ, Q squared. We toss it a third time. AAA, AAB, ABA, ABB, BAA, that's the sheep probability, BAB, BBA and BBB. Probabilities, PQ, P squared Q, P squared Q, PQ squared, P squared Q, PQ squared, PQ squared, P cubed. Oh, what's the heck? Let's try and squeeze one more in there. Oh, famous Swedish group from the 70s. And then the very last one is someone who's trying to sound silly. Anyway. Probabilities. B to the 4, PQ cubed, PQ cubed, P squared squared, Q squared, PQQ. Oh, that's hard to say. Now, if we have a look at each of those, but we're not concerned with the order, okay? Then one event, probability A was P, probability B was Q. Two events, probability of AA, P squared. Now, probability of an A and a B, but we're not concerned with the order, would be 2PQ. And then BB, Q squared. Three events, P cubed, 3P squared Q, 3PQ squared, it's Q cubed. Four events, again, we're not concerned with the order, but we start to recognise a pattern here. And again, it's not a coincidence. It's the binomial expansion. Because really what we're doing is we're saying, well, the two probabilities add together to give one. So P plus Q would be all the probabilities. And we're repeating it over and over again. So if we repeat it twice, then all the probabilities would be in P plus Q times P plus Q. P plus Q squared. And cubed, and so on. So we get exactly the same coefficients as we saw in the binomial theorem. Thus we can, rather than draw a complete tree diagram, if I've got an event that's been repeated n times, and I know the probability of something happening is P, and therefore the probability of happening, something not happening would be 1 minus P, let's call it Q, then that probability that it occurs exactly K times would in fact be our general term for a binomial expansion. So probability that x equals K, which means x will occur exactly K times, will be NCK. P is going to be to the power of K, so the probability of it happening to the power of K, probability of it not happening to the power of N minus K. So we've got a bag which has got 30 black balls, 20 white balls, and as I say, it's important that these are with replacement. So we're going to draw 7 of them. What's the probability of all black? Well, I suppose I don't really need to use the binomial probability idea for this one, because if it's all black, then we're going to have, well, 3/5 just to the power of 7. But of course, if we have a look at it in our binomial theorem, I'll get 7C7, well, that's 1. Probability of it happening to the power of 7, 3/5 to the power of 7. Probability of it not happening to the power of 0, so 2/5 to the power of 0, which is 1. So yes, indeed, we get that 3/5 to the power of 7. Now, in unsimplified form, 7C7, 3 to 7, 5 to 7, if we were to work that one out, because those numbers aren't that big, I suppose, 2,187 on 78,125. But the advantage of looking at it in the binomial theorem is now we can say, well, hang on, what happens if there's only 4 black ones? Okay, if there's 4, then it'll be 7C4, probability of it happening to the power of 4, probability of it not happening to the power of 3, So unsimplified, it would be 7c4, 2 cubed, 3 to the power of 4 over 5 to the power of 7, which tidies up to be that, 4,536 over 15,625. Okay, try another. We've done some surveying, and we know that at an election, 30% of the voters favoured party A. So at random, we're going to select 5 voters. Probability that 3 of them favoured A. So X is going to be the number of people favouring party A. Probability that X is 3A, well, that'll be 5C3. Probability of it happening is, well, they said 30%, so 3/10. It's the power of 3. Not happening to the power of 2. Again, there's the unsimplified version. That one works out to be 1,323 out of 10,000. And we still get these sort of traditional questions you might remember from probability where they go, oh, majority. Well, majority would be 3 people, 4 people, or 5 people. So we just work out each of those individually, add them all together. Again, unsimplified is that lovely expression. If we work it out, there it is, 4,077 on 25,000. At most 2 favoured A, again, go back to your probability idea. Well, actually, at most 2 is the complementary event of majority favouring A. And we've already worked that out. So we know we can go, hang on, less than or equal to 2, that's going to be the same as 1 minus X is greater than or equal to 3, which we just worked out. So to save some time, I can just subtract that probability from 1. So basic probability ideas, of course, still come into play here. All right, let's have a look at an actual exam question. So 2005 paper, this one comes from. There are 5 matches each weekend in a football season. So Megan's taken part in the competition. She's going to get 1 point if she picks more than half of the winning teams for a weekend, 0 points otherwise. And we know that the probability that she correctly picks a team is 2/3. So the probability that Megan gets 1 point for a weekend is 0.7901. Okay, so X is going to be the number of matches that she picks correctly. Probability that X is greater than or equal to 3. And she has to pick more than half of the winning teams. So 5C3, 2/3 probability of her picking correctly. It's power 3, 1/3 squared. 5C4, 2/3 to the power 4, 1/3 power 1. And of course there's the possibility that she picks all 5 of them. Unsimplified, bang it into our calculator or our phone. We could be using that, of course, as a calculator, which is what I, of course, assumed you would have been doing there. 0.7901. Hence find the probability that Megan earns 1 point every week of the 18-week season. So now I'm going to, new question, Y is now going to be the number of weeks that she does earn a point. So we're saying, what's the probability that Y is 18? And we just worked out the probability of Y happening is 0.7901. So therefore, not happening is 0.2099. Probability of happening to the power of 18, not happening to the power of 0. And we get 0.01 to 2 decimal places. Find the probability that she earns at most 16 points. 16 points. Well, I'm going to do that complementary. Because, look, at most 16, she could earn 0, she could earn 1, she could earn 2, 3, 4, 5. Lots of probabilities that are happening. Easier to work out the complementary event, especially since we've already worked out 18. So we now also need 17, and we get 0.92. 2007. We know that in a particular city, 10% of the population has green eyes. What's the probability that 2 randomly chosen people have green eyes? Well, now it's just, 2 green, they're both green, so 0.1 times 0.1, 0.01. What's the probability that exactly 2 of a group of 20 randomly chosen people have green eyes. So this time I'm going to say, well, X is the number of people with green eyes. Probability that X equals 2, 20C2. Probability of it happening to the power of 2. Probability of it not happening to the power of 18. So we have 0.285. So you can see these questions that basically you just got to work out the probability of something happening and then apply it to the binomial theorem. What's the probability that more than 2, so more than 2, 1 minus the probability of less than or equal to 2? Oh, we're going to take away 2 people, 1 person, or nobody, 0.32. I think the biggest mistake people make with these binomial probability questions is forgetting the binomial coefficient, the 20C2, the 20C1, and so on. So 10J, which actually is in our permutations combinations chapter in the book, it's actually the last bit of that topic, which of course we had to leave out until we did the binomial theorem. So now we can do it, of course.